Okay. Hi, everyone. Welcome to the October ALT2 meeting. Just to remind everyone, the meeting is recorded, so just be careful with what is it. So today, we had a meeting in September. That one was delayed, was September 12th, so we only had about 3 weeks. So this meeting came up very quickly. So the results, as I say, not everybody had a lot of full updates, so it's supposed to be a very short meeting today. So I'm going to do a little introduction again, just to remind everybody the status of where things are, what's ongoing. And then we're going to have an update from Angle with regards to the in vivo efficacy. So very brief update from Angle. Then we're going to have Jean for giving us an in vitro update. He just came back from vacation too, so he had just very few experiments, so that update will be very short. But we were lucky, we have some of our star students, and my research fellow is going to give us some updates on some of the fantastic stuff they have been doing. We have a master student, Mahapri. Yep, she's been doing some nice work. One of the actionables we had in the program was to come up with this M4K permeability experiment. So it was a nice surrogate for BBB penetration studies, and so we managed to get that to work, and we did evaluation of a couple of compounds, and she's going to take you through that and show you a nice analysis that she has done. And then Lisa is a research fellow at ICR, and she also have done some computational analysis of some of our compounds, and she's very anxious to give us an update today. So looking forward to all of that. So without further ado, this is not going forward. Okay. So yes, I'd like to remind people again, we're dealing with a disease, that disease is driven by ALK2, and we decided to take on the most difficult one, DIPG, which is actually an area of great need. I also have at the end, I just put this slide in to remind people we're trying to develop a PD, and so it's based on the third picture to your extreme right. We're doing this hepcidin model. We're hoping we can develop that as a PD model going forward. Let people know again, these are the 5 lead compounds that we're currently looking at. The first 3 has very, very good CNS penetration. The other 2 has very, very good herd profile. So we're trying to kind of figure out which one of these is going to rise to the top. I'd like to remind people that the profile for these compounds are excellent. They have decent favorable profile. More important, the in vivo properties are very, very good, as demonstrated by the mouse PK here. Most of these compounds have overall bioavailability over 60%. Okay, that's very rare sometimes in development programs.
What's the timeline for the SIP invention for 2162?
So we're getting that PK. We actually hadn't budgeted for SIP. It's something we have to do. I realized that I was going to the table. That's the last thing that's left for that 2113 since it was left. So that's an action we actually have to follow up on front of. Yeah, but we're getting the right PK. So I thought I'd just update the team with regards to some of the current actions ongoing. So with those 5 lead compounds, we've decided to embark on making 50 grams of each of them. We had 50 grams of 2009 already. And the whole purpose of that amount was to continue to hopefully, whichever one rises to the top, we want to do some tox analysis and some probably potential dog PK, some higher species PK. So GL Chemtech have taken on the task of scaling up all of the lead compounds. But we got a recent update from them that because, the 2 compounds, 2234 and 2236 actually, that chemistry route that they mapped out involve a cyanation. And because that's a regulated substance, it's going to take a little bit more time before they get larger quantities of that cyanide agent. So they feel like those 2 compounds might be delayed until probably next year. But the CNS penetrants 1117 and 2163, they feel like, they're running a little bit behind time, but those might be on track to be delivered this year. So we hopefully have enough of those compounds ready to go. We added 2163, the compound that's showing very nice efficacy in a lot of the DIPG lines. We added that one to the shortlist very late. And so we are now catching up with data for that. So we've sent the compound out for rat PK and dose mouse escalation study at Pharma, so that's ongoing as we speak. Angel is going to give us an update as to the efficacy study that's ongoing. And then I think Diana from Chris Jones' lab, I think they had done some acute toxicity analysis in their model. And I think hopefully they're probably gearing up to start the study there. Another important aspect, again, for the project is we have been trying to understand a lot of these DIPG lines. That's being one of the Achilles heel of DIPG. They are not good models, and so a lot of the experts in the field are trying to understand these cell lines, what's driving them. So if we can understand which of those lines are ALK2 dependent, we might be able to develop even better models for targeting ALK2 mutants. And so we are thinking of a couple of approaches, CRISPR, thinking of PROTACs. And as a result, so in addition to the backup effort from CRL, Sue and her team looking for backups based on the blueprint series, they're also looking into PROTACs. We have made up for PROTACs here, but they're also looking into some PROTACs. We're hoping that those tools would actually help us, decipher some of the mechanisms of action in some of these cell lines, which ones are driven by ALK2. Another important thing I just mentioned is we're doing this PD study using serum hepcidin. We are running a pilot right now at CRL. That experiment was started, and so we're hoping to get that data soon, to get a feel whether or not this would be a viable path forward for PD studies. And again, because this is an area of real need, we kind of envision long-term that combination strategy to treat the disease is going to be the way forward. So we're continuing to explore potential combinations with some of our leads, and so some of those studies are ongoing. And lastly, just to remind people, the CTIP grant that we had driving most of this project, it's now due for an update. We got a letter from the Secretariat saying that a progress report is due on October 18th, so I might be bugging a couple of you for information as I need going forward. Okay, so those are just some of the current actions. If anybody have any questions or want to suggest anything that's left out for now, okay, feel free to do so. And I thought I'll finish up with, in terms of the deliverables over the time of the grant, we have met a lot of our deliverables, and so these are the remaining deliverables. I thought now is a good time to just remind the team based on our commitment to the grant, and so we can better gauge which ones are we going to meet, which ones we want. So I wanted to give the team a better feel for that. So for the remaining actionables for the grant, one of the things we said we were going to do is to demonstrate dependent modulation of PD markers in vivo. So we end up now using the hepcidin model. That's what we're using. So that's ongoing. Hopefully that could actually give us some ideas whether or not this is a viable path forward for an in vivo PD marker for ALK2 engagement. The other thing we had promised them 2 years ago was a CNS biomarker ex vivo using phospho-SMAD. We haven't done that, and that might seem as a fast stretch right now as we go along, but if people have ways of making that happen before, like in the next 2 weeks, that would be great. Okay, but I don't think we'll be able to do that. The other one was to complete evaluation of xenograft survival and tumor burden, so that's what Angel and Chris Jones are doing now, so they're getting close to those. Okay, and then assessing acute toxicity in xenograft model. Diana has done an acute analysis. We have also taken some of our compounds before we went into the xenograft and do a bit of acute tox analysis. So I would say that's complete. We know the animals tolerate 100 mg/kg, 50 mg/kg. So I think that we have done that. Now, with regards to some of the backup efforts, we thought that we promised that we'll make about 15 new compounds from the backup series from the last update. And so that's ongoing. I think that's going to include both the blueprint analog, and also I'm going to throw in some of the PROTACs. Okay, and then at that time, we also promised them crystal structures of the backup compound. Now, I know we have ramped down on crystallography, so we don't know if that's a goal we actually still going to commit to, or we actually just shut it down. I'm going to leave it up to the team to decide whether or not we submit couple of compounds on the backup series for crystallography, or we could just abandon this goal. We're not going to pay any price for that and focus on the other stuff that's important. Okay, and I just put this timeline chart just to kind of remind people where we came from in August. Right now we're doing the efficacy, we got the scale-ups ongoing. You could see a lot of the other development stuff we kind of push after the timeline of the grant, things like dog PK, dog telemetry, more elaborate rat tox. And those have to wait until we get enough compounds to. So just kind of put into context some of the things that we want to get accomplished for the development goals. And I also want to open up the question that I think Alex did send an email out the other day, was asking whether it's possible to extend the grant out until March of next year. And so although that's a possibility in the grant, they give you an option of extending the grant at no cost. They won't give you any extra money. So if Owen still has a lot of cash in hand, we can either have a party or we actually go until March 28th.
Well, since there's no line item for parties on the and that doesn't quite meet the overhead. No, so we'll probably be getting together to formally request late this week and early next week a no-cost extension. And a couple things as we get close to the end, not least of which is the fact that GL Chemtech won't be delivering drug until January next year. And there are still a couple experiments we'd like to get done. And we need to, as a team or get together and talk about which one of those experiments we can do. I'm a little biased towards taking a look at a little bit of the tox, just to see how clean this is as we move forward and really do for one of the compounds, whichever one we think, just see if anything comes up, because our next step is to get into kind of a preclinical selection, and if there is an indication of some tox, then that will change our preclinical program about what we have to experiment, what we have to look at, etc. But anyway, so go ahead, yes.
This is probably a silly question, but how does this no fund extension work? Are you spreading out the existing funds a little bit longer? You're not actually you're having to find new funds to fund. This
will just be the fact that we do have some excess funds, and that's why we'll have to decide which one of these things we could get done during this time. It was the original hope that with the GL Chemtech compounds, which we were hoping to basically have now, to be honest, that we would enter into one of these studies now, and then we pretty much wrap everything up on schedule. But because it's not taking longer, we haven't done that experiment, which we're supposed to do now. Does that make sense?
It makes perfect sense.
So yeah, no more money, just we haven't spent it yet.
Are there plans to kind of get this moving forward, like with another grant, other sorts of funding?
Yeah, we actually, that's a very good point. Yeah, we have actually had some conversations with, and we're fairly going down the line with our lead compounds going into an advanced ADME and tox set of studies that could be done to pull out in front for everyone. NIH has a program we've been talking to them about. We would still have to do the efficacy side from our side. Right now is what we're talking about. So they would move that forward. That would be about a 12 to 16 month plan. And then from there we'd have the the ultimate selection for an IND candidate, hopefully. And then the NIH program allows you to reapply based upon the success of that that they will do the whole IND application. What I'd like to do at the same time is find funding for more pharmacodynamic work and also the backup series and keep those programs moving along. In case, as everyone here has done drug discovery, we find that the lead series, despite everything we've seen to date, hits a dead end. And then we've had something to go back to.
So coming back to David's point, right, with the March extension will just allow you to expend, spend the money you have right now.
Correct.
All right.
So Owen, sorry, Matt. It's Rima. Owen, maybe when we meet, we can discuss what else you feel needs to be done on the backups and what that cost would be. I think we could, we'll need to share that with the committee as well, I think.
Okay.
Like present that to them, right? To say, here's what else needs to be done. So that we're clear where the project sort of, what additional critical things that we feel are still needed on the project.
Sure. And how far behind the lead series is the backup series?
Exactly.
Yeah.
I think that would be good if we could articulate that as well in our presentation.
That's a good suggestion. Thanks.
Yeah. Okay, good. If there are no other burning questions, let's go on to Angel's update. Angel, are you there? Hello?
Yes, I am here. This is Angel.
Okay, how are you doing?
Hello, everyone.
Do you want me to, I have your slides. Do you want me to drive them or you want to share? How do you want to do it?
I would like to share my screen, please.
Okay. Just stop share or share? Do I go to new share?
Stop your
Huh?
Stop your share. Yes.
Stop this one?
Yeah.
Yes?
And then you, then he
Okay.
can do.
You should have control now.
Ready.
Awesome.
Let me see. Can you see it?
Yeah, beautiful.
Okay. So, hello everyone. I want to give you an update about this study. I think we still have to wait a few more weeks, maybe 4 weeks more, to finish the study. This is a study made with the DIPG model number 7 from Barcelona. This is a model with the ACVR1 mutation, R206H, with a 100% take rate. Median survival will be, we expect to have 70 to 100 days if the treatment doesn't work, hopefully more. And this is a very diffuse and infiltrative model. And we have done this, Leire Balaguer, my student, and myself. So we have used not SCID mice for this study. We inoculated the tumor by mid-July, and we started treatments 1 month later. We have 4 groups in the study. One is the control. We have treated this control with vehicle. Second group is 100 milligram per kilo for 4 weeks. Third group is 50 milligram per kilo, 4 weeks too. And the fourth group is 100 milligram per kilo. And we will try to keep this for 8 weeks. And we are going to do two types of studies. The first one is that after we finish these treatments, 4 weeks or 8 weeks, we will kill 3 mice from each group, and we will take samples to evaluate what is the tumor burden at that specific time point after treatment. So we would expect that there is lower tumor burden in the treated mice than in the control mice. And the remaining mice will be used for the survival study, and the criteria we used for this endpoint is 20% weight loss due to disease. So with this approach, we will have 9 to 10 mice for groups 1, 2, and 3 that will remain untreated until after treatment, until endpoint. And the other 10 mice from group 4 will continue receiving the treatment for 4 more weeks. So this is the samples we have collected like 3 weeks ago, almost 3 weeks ago. After the end of treatment in groups 1, 2, and 3, we have collected 3 brains and 3 plasma samples, 1 of each animal, okay? So these samples are available for several things. First, to study how much tumor is in there. We can do that by immunohistochemistry, or we also measure how much ACVR1 mutant DNA is there, so that we can compare treated and controls, okay? And we do that by digital PCR. But I have also these samples available for you guys in case you are interested. I could ship samples for a PK study because these animals were killed 2 hours after the last dose. So that's supposed to be like a steady state. So in case you are interested in these PK samples, let me know. I will ship them to you frozen so that you can analyze if you have the ability to do this, okay?
Yeah, Angel, that would be nice actually. If you can ship them to us, we'll do the analysis.
To Toronto?
Yes.
Yeah.
Okay, excellent. So we will do that.
Yeah.
So this has been the scheme of what we've done so far. Tumor engraftment, 32 days for the engraftment, treatment start 5 days, 2 days off, the weekend, 5 days, 2 days off. We stopped treatments here because we didn't like the way the animals were, like with the skin and, or I mean the hair, and they were losing weight and they looked a little bit damaged by the treatment. Actually, we did a mistake here and we didn't give the vehicle to the control group, but we started right here and we observed the same, exactly the same observation. So the vehicle is causing this little bit of damage in the animals for the aspect of the animals and the hair and the weight loss. So this is the time we collected these PK/PD samples. Regarding the survival, so we are now at day 75. This is yesterday. So as you can see here, these treatments, these are the 2 periods of treatments for groups 1, 2, and 3. These 2 groups, the 3 groups were treated during this period. Now here, all groups stop treatments and group number 4, which is 100 milligram per kilo, start again, okay? So what I like to show you here is that if our endpoint for the study is weight loss, which is the only objective measure that we can do. So now the control is behind the treated groups, which I like to show, but still have to confirm, of course. But this is something interesting to me, and hopefully we will have the expected results, although still has to be confirmed. And this is all I have to show you today. Everything is going well. So again, groups control and 2 and 3 will not receive more treatment. So we are just waiting for them to achieve the endpoint, and group 4 is still receiving treatment. Okay. That's all I have.
Sorry, on this chart, just remind me, the control group, when did they start receiving the vehicle again?
I think they started at right here at day 42 or so. You see, they start losing weight here. This is due to the vehicle. So initially I was concerned about this mistake, but now I'm fine because I think they just reached the levels of the others. So after we stopped here, treatments and vehicle, they just recovered a little bit. But I like to see that, for example, this group recovers some weight, or the green group recovers some weight, and the controls are still losing weight. So maybe this is good because they are sick already, and that's why they are still losing weight. Now, for this period, we have decided not to give vehicle to the controls because we prefer to have groups 1, 2, and 3 safe, and we don't want to lose we don't have to lose the ability to interpret the data, because if the group number 4 is still losing weight due to treatment, then if you give also vehicle to the controls, it's very difficult to look to see whether they are sick or not. Do you understand? So we have decided to stop treatments here for groups 1, 2, and 3, including vehicle. Okay.
Okay, that is it.
So I have a question.
Yeah.
Ahmed, should we start looking at alternative formulations?
I think so. Yes.
We started discussing that already.
We discussed about that, and I think we'd like to do a bridging PK data with the methyl cellulose formulation. We discussed about that, and that is ongoing, and we'll do it as soon as we can.
Yeah, because in my hands, the previous studies. In my hands, previous studies with the controls, they just keep on gaining weight, and they stay at the maximum weight for example, during this period, and then when they start to be sick, they lose weight. So in this case, they just start losing weight due to treatment, to what they call. So we don't want to do that.
But so Owen, I guess part of this exercise will probably entail coming up with a new formulation and rerunning the study, right?
I think that would be ideal right now, because I guess with the data that I'm looking at here, I'm struggling to figure out what's really happening here. Is it just the vehicle is causing all this, or what's the disease portion and what's the drug portion?
Yeah. Now, of course.
It looks like the vehicle has the biggest impact on the study.
Well, but there is if you look at the brain history.
Yeah, he's going to look at
the brain, and then that will answer some of that, right? So that'll be the.
But no matter what, you're going to have another efficacy study, depending on what you decide to do and how you design it. But you need to have that because.
Well, and the other thing is, obviously, we have in this, it appears that the vehicle is causing, a lot of illness for the mice. So if we wanted to do a longer study, we can't really do it with this vehicle because we might be making the mice so sick we can't continue dosing, etc. Plus, if we want to do a safety study or a tox study, it's, as well, it's obviously an issue that's floating around here.
I mean, I'm thinking too, like, I think Angel did mention that, these tumor models, they tolerate saline very well. So you got methylcellulose, you could probably make 1 or 2 salts, see if they dissolve in saline.
Yeah.
At the doses you want, at least. So we know that vehicle is already tolerated. Methylcellulose might be okay.
Yeah, methylcellulose would be most likely way to go because it's PO dosing, and most likely I'm guessing right now, but we can try a few other, as you said. We can try a few other, but most likely to be methylcellulose.
But Angel, I just want one thing. Angel, this has been fantastic. I mean, it's really. I really want to appreciate, thank you for the work that you guys have been doing on this study, and thank you very much because this is really helpful about leading us in a number of directions and improving the program.
Yeah, and to add to that, I mean, the vehicle effect, we did not anticipate that at all. So this is very, interesting finding here that we have to address. And we wouldn't have figured it out if we weren't doing the study. So this is very important.
So one question, please. Did you do the bioavailability study with this same vehicle?
Yes.
Yeah. Okay. So maybe we'll do another one if we choose to change the vehicle, right?
Yeah, we'll do PK. That's why I said we'll do a bridging PK. Like, PK studies, it's very acute. You only see effects of vehicle when you do these long-term studies. And we have done projects in the past where we've actually seen maybe depending on the type of tumor. Sometimes the animal gets sick with the tumor that's injected, and then you see the combination of that and vehicle. So, I'm sure this is the first time you've used this vehicle in this model.
Yeah.
So this is a kind of a learning curve for us. Yeah.
Nothing?
Hi.
This might have been mentioned before. What is the vehicle?
It's PEG, DMSO, water, and
PEG is the guilty here. I think PEG is the bad thing.
You think PEG is the culprit?
I think so, because we have some experience with PEG and we didn't let it. PEG 300.
Okay.
Yeah, we were thinking it was DMSO, but it's okay. But we can
we'll change that.
Change it, and we'll do the breeding PK to figure out where we get the comparable exposure, and then we'll take it.
Yeah, we'll do some formulation work and come up with some vehicle options actually.
So I have a question for Ahmed, just from a timing perspective, because we have the committee presentation, right? Maybe thinking about whether we can generate some of this data or at least some preliminary information that would lead us to believe that we can have a different formulation with a path forward. I think would be very, very helpful going into the committee discussion.
If we can get the salt and if you have the compound availability, I can prioritize that over the other project. As you know, we regularly have mice and rats coming in. We can prioritize it, and then that can go.
I think that would be great.
Yeah, let's plan on coordinating that maybe offline with.
Okay.
Okay. Thanks.
Okay, thanks, Angel. This is great. Thank you.
Thank you.
Yeah. Oh, sorry. The brain samples. When are they being analyzed?
He's going to ship them to.
Oh, we're doing the brain. No. The plasma. We're doing the plasma.
We're doing the plasma, but it's actually a good point. Like, do you want us to also is it can you share some of the brain with us? Then we can also look at the brain if it is
penetration, like PK.
Yeah, but I think histochemistry is more important.
Yes.
I mean, we know the compound goes in the brain.
Yeah.
If we have enough on board in plasma, then it's good. But if you can share the brain after the histo, then we can look at the brain too.
I think we should just do the histo for now.
Yeah,
Yeah.
we have both. We have paraffins and we have frozen. So I will send whatever you need. You need frozen, right?
Yeah, I need the frozen. I don't need the paraffins. Yeah, just
Okay,
the frozen brain and the plasma. Then we can look at the brain concentration and also look at the plasma concentration.
Yeah, happy
Okay.
to. Yeah.
Oh, well, thank you, Angel. I will
Thank
use
you,
a coordinate
Owen.
on that.
Yeah.
That's,
And so that would be total brain, or actually?
Well, he's going to take some of the brain for the histochemistry, right? So we're going to get some of the brain. So whatever I get, if I get around 200 milligrams, should be good enough.
we'll coordinate with him.
Yeah.
And if there's, I have no idea how much brain
Cut to
food,
me.
et cetera, and go from there. I'm actually, because of the weight loss seems to be so influenced by the vehicle, I really want to see what his brain histology
Yeah, that's more important.
states. That'd be more important.
Okay, the only caveat I see, from what I've learned, I think I heard Cynthia Hawkins talk a lot about, the tumor in the brain and stuff, and how the brain stem around the pond is a lot different to the rest of the brain. So if he's taking the pond to look at the tumor in the pond, then is he going to have enough brain? Do we want to see, is compound in the pond, or is it in the brain? You can have compound in the brain, but not a lot of it is getting to the target. So
We can talk offline. I think they'll consume the data we have right now. I think his experiment is more important than your experiment. So, if Angle uses up all the brain or there's none left, so be it. That's the more important, data point.
I think
Okay.
that wherever sample we choose to ship to you, all the controls and the treated mice, you will have the same portion of the brain. So that's the
Okay.
important thing. No, not, sorry, I didn't mean that, but you will get like a portion of the brainstem, probably the right or the left, and we will do the other studies with the remaining.
Okay, sounds good.
Okay, good. Bye.
Thank you. How do I get back now? Share?
Share. Yeah, you share.
What do you want to share?
Thank you. Yeah, so we're back in business again. So up next, Jean-Paul. Yeah. Jean-Paul is online? Hello? Jean-Paul? Uh-oh.
They're in line. I can see them.
Huh?
They're online.
Okay. I don't know, maybe you have your phone on mute. We can't hear anyone from Oxford.
Alex? Jean-Paul?
Yeah, can you hear us now?
Okay, it's very low still. You might need to turn up your phone volume.
Still can't hear you.
Yeah, still can't hear you. It's very low.
Is it better now?
You're still very... Hello?
No, Alex, I can just barely make out.
I think we'll have to log out and log back in again. An update came up on the computer and it must have messed things up.
Okay.
Okay. Well, can you do that? Can we do someone else's presentation? We'll come back to their presentation once they log back in.
Yep, okay. Okay, so up next is Sani, Matt.
So, Matt.
Yes.
So,
okay. Yeah, so just use this if you want, make it easy.
yeah. Do you want to introduce yourself as well?
Yes.
Including to me?
Yes. So I'm Mahak Sani. I'm a master's student at OICR, and today I just want to update everyone on what I'll be doing or what I've been doing for the last few months or so. So just to preface the presentation, I know everyone here is well aware of the rationale and background for this project, but as a new student, it's really good for me to be aware of the big picture. So bear with me while I go through that in the next slide. There we go. There we go. All right. So, of course, for this project, what we're trying to do is develop small molecule inhibitors of the receptor ALK2, which is known to be mutated in the pediatric cancer, diffuse intrinsic pontiglioma. And normally for cancer, we have 3 treatment options: surgery, radiation therapy, and chemotherapy. However, due to the localization of DIPG within the brainstem, which is a critical region of the brain, surgery is often not an option. Moreover, this cancer is infiltrative, meaning it affects the surrounding tissue. And so even if surgery was performed, complete removal of the tumor would pretty much be not possible. The second option is radiation therapy, and although it's initially effective, it is often followed by recurrence of the cancer within a few months, and yet it has been the standard of care for the past 50 years or so. And this is not because we haven't been trying to develop new chemotherapeutic agents, it's just that they haven't been as effective. And so what we have here is a huge unmet need to develop new treatment options for DIPG for a disease that has extremely poor prognosis. And this is where we come in. And you all know this better than me, but to develop an effective chemotherapeutic agent, what we need is to tackle issues such as potency, selectivity, and toxicity. But in our case, in particular, what we're dealing with is an issue of permeability. Not just gut permeability for most oral compounds, but the permeability of a compound in the blood-brain barrier. So what we need to do is select compounds that are able to permeate the blood-brain barrier. And for this, normally we do animal testing and we measure the concentration within the brain. However, that can, of course, as you can imagine, be costly and also time-consuming. So the goal of my project is to be able to predict the in vivo blood-brain barrier permeability using in vitro data. And for this project, I have some aims to develop this in vitro assay known as MDCK2 assay is one of them, and identify MDR1 substrates using these 2 cell lines over here, which I'll explain more later. And hopefully, by doing this assay, we can optimize lead molecules and improve the progress from preclinical to the clinical stream. Now, MDR1, you might know it better as PGP, is one of the main transporters that's responsible for effluxing drugs out of the brain, which is why we're choosing to study this transporter in particular. The second aim is to do a comparative analysis of this new assay with other models, such as the in vitro CACO2 permeability assay we currently do, and also an in silico model such as Swiss-ADME, which has shown quite good potential for predicting BBB. And last is the most important aim of my project, which is to determine the in vitro, in vivo correlation using this MDCK2 assay and evaluate some lead molecules that we know the in vivo data for. So I just want to go over the experimental setup just a little bit. When I culture the MDCK2 cells, I place them into a 24-well plate and they grow on a transmembrane layer as a monolayer, and they orient themselves based on polarity to the apical and basolateral side. So the apical chamber, or the apical side, represents what would be the blood, and the basolateral side represents what would be the brain tissue. And so depending on how I dose the compound, I can figure out the permeability of a compound going from the blood to the brain, or vice versa, from the brain to the blood. And from this experiment, I can find or measure 2 values. First is the apparent permeability coefficient, which is kind of like the speed at which the compound goes from the blood to the brain or brain to the blood. And the second is the efflux ratio. So this tells me how much of that compound is being pushed out of the brain. And in this experimental setup, I have 2 cell lines that I'm using. The MDCK2 cell line is a wild-type cell line from dog species, but we want this to be relative to humans. So what we've done is purchased a cell line in which the dog CMDR1 gene is knocked out, and then the human MDR1 gene is reintroduced. So we have a more relevant cell line. And of course, we want to test and make sure that this is working properly, so I did a Western blot analysis, and of course, the knockout does not have the human MDR1, and the knock-in does. And when I quantitate it just for a relative value, I can see the exact same thing. In this case, we're using the CACO2 cell line, which is a human cell line, as a positive control because it should express human MDR1. So we know that the antibody is working well. So moving from that, what I can do with the cell lines and experimental setup is I can determine whether a drug is an MDR1 substrate or not. And from this, for example, if I have two drugs here, drug 1 and drug 2, if I dose them within the knockout cell line, they should have an apparent permeability and pass through. However, if our compound is an MDR1 substrate like drug 1, as soon as it goes into the cell, it will be kicked right back out by MDR1, the transporter, and that will decrease the apparent permeability of that compound. However, if the compound isn't a substrate, it can, the relative value between knockout and knock-in won't change. And so using this, I can identify which compounds that we have or that we produce are MDR1 substrates or not. And I can also measure the impact of this transporter on the compound's permeability by quantifying it using the efflux ratio. So then I can rank order any of our lead compounds based on this value, which is what I've done with these 8 compounds. So I have 3 compounds from the blueprint series here, and I have 5 compounds from the pyridine series here. They've all been tested in vivo, so that's why they were selected. And I tested them within the MDCK2 assay. So what you're seeing here in the blue is the average knockout efflux is the average efflux is a knockout cell line, and in the orange you're seeing the average efflux in the knock-in cell line. So the greater the efflux value, the greater the efflux value, the worse technically that compound is. So for example, M4K 2256 has a really high efflux here in the knock-in cell line. So I would predict using this assay that the BBB penetration for this compound would probably not be that great. However, a compound like M4K 2117, which doesn't seem to be affected by the presence of MDR1 or not the presence of, or without the presence of MDR1, I would predict that this BBB penetration data would actually be really good. And in fact, M4K 2117 out of these 8 compounds has the best BBB penetration data that has been seen. So we can use this assay like this, and once I developed and seen that this was working, I could do a comparative analysis of what we've been using so far. So this is the CACO2 data for those 8 compounds and in the graph more. And I can see that there's actually a quite nice correlation between the CACO2 permeability assay and MDCK2 with R square value of 0.914. And so that just reassures me that this assay is working quite well. And secondly, I want to compare it to an in silico model. So this is an in silico database known as SwissADME. It's a web-based software in which it gives you a bunch of information based solely on the structure of the compound. So it can give you physical chemical properties like lipophilicity, water solubility, etc. But of importance to us is the pharmacokinetics. So what it tells you, or what it predicts, is whether that compound would be BBB penetrant or whether that compound would be an MDR1 substrate or not. And it gives you something quite interesting, something called an egg boiled plot, or boiled egg plot, excuse me. And it looks like a boiled egg, as you may imagine. And within this plot, within the white region here, any compound in this area is predicted to pass the gut. And any compound that is within this yolk region here is predicted to pass through the blood-brain barrier. So you can see most of our compounds fall within this area, which is quite nice. But also it correlated quite nicely with the MDCK2 data, and in particular with the in vivo data. So what I've done here is just ignore the blue points for now and focus on the green if you can. The radius of these points is the C-brain C-plasma ratio at 4 hours, 10 milligrams per kilogram. And you can see here that most of our compounds that are within this yellow area actually have a better C-brain C-plasma ratio than the ones that are outside. So that means that this software or this in silico model might actually be a really good predictor of what compounds might have good BBB penetration. If you focus back onto the blue points, these are compounds that I've tested in the MDCK2 assay, but do not have in vivo data, or did not have in vivo data for at that time. And I would have predicted that OSCR 18943 or M4K 2163 would have really good BBB data. And actually, recently, it has been tested, and it has the best BBB penetration data out of all the compounds we've tested for ALK2 so far. So this shows me that this in silico model might actually be really good for the ALK2 series in the future. So moving on to my last aim, which is the most important one. Of course, we have these 8 compounds once again. And what we've done is tested them in vivo. So we did a thorough PK analysis in non-skid mice, dosed it IV with 2 milligrams per kilogram or oral dose at these values. And of course, we get things like clearance, half-life, and bioavailability. But importantly, we looked at the BBB data. So these mice were dosed at 10 milligrams per kilogram or 100 milligrams per kilogram at 2 hours or 4 hours. And then their brain and plasma concentration was determined, and their ratio was determined from these values. And this is what I'll be looking at in the next few slides. So I've rank ordered these 8 compounds based on the BBB penetration, and we see that M4K 2117 has the best C-brain C-plasma ratio compared to all the other compounds, even our lead compound here, M4K 2009. And whether that is in 10 milligrams per kilogram dose or 100 milligrams per kilogram dose, it stays the same. M4K 2117 has the best data so far. And then what I did is compare it to the MDCK2 assay. So what I was expecting to see is as that ratio decreases, the efflux should increase because that means more of that drug is being removed from the brain. However, you might see from the color coding itself that this is not what I observed. The correlation was actually quite unfortunate, R-square value of 0.158 for these 8 compounds at a dose of 10 milligrams per kilogram 4 hours. However, in 100 milligrams per kilogram dose, it seems to be a bit better. And I'm cautious with this because there are only 5 points. So it does have a nice R-square value, of course, but there's, again, only 4 points. They are well dispersed, but it would suggest that maybe this assay would be better predictor at 100 milligrams per kilogram dose rather than 10 milligrams per kilogram in the future. So with that being done, I wanted to identify any other correlations that I could. So I input all the data that is related to these compounds into a software called Data Warrior. And then I obtained something called the Pearson correlation or coefficient, which tells me how good the linear correlation would be. I then put it into Excel, so the darker the green, the better the correlation, and if the number is between 0.8 to 1, it comes out as red. And from this, I found something quite interesting, which is actually back to our KCO2 permeability assay. So we have our KCO2 permeability going from the brain, going from B to A, so basolateral to the apical side, and the C-brain and C-plasma ratio at 2 hours for 10 milligrams per kilogram. There's actually quite a nice correlation, which would suggest that this might be a good readout of any compounds that we have to test in vivo in the future. And what I'm currently doing right now is to test more compounds, rank order them as best as I can with the MDCK2 assay. So these are some new compounds that have been made, and we tested them with KCO2, and I'm testing them currently with the MDCK2 assay. They're selected based on the cell-based assays that we have. And also, I put them into SysAdme so I can get a general idea of what I expect to see with these compounds. So for example, this compound over here, I probably don't expect this to have any good permeability, so I might not even test that in the future. But these compounds, I have, but if I was using this as a predictor, I would not test this in the future. But these compounds in here would tell me that these compounds are worthwhile testing. And secondly, we have some more compounds that have been tested in vivo with BBB data, and I'm updating that correlation so that I can identify and aid in predicting the BBB data. And I can also populate the plot with more data with those data points, but also because we can't run every compound in vivo, I want to select some compounds from the literature and run it within this MDCK2 assay so that we can actually validate these correlations. And hopefully we can get to our goal of predicting a compound's in vivo BBB penetration and better select and optimize these compounds for the treatment of DIPG. And I'd just like to acknowledge the people that have helped me out throughout the last few months.
Yeah, it's very good. Nice job.
Thank you
Good
very
job,
much.
yeah. Good job.
Good
the 10 mg dose is probably more real than the 100. I'm wondering at the higher dose you end up saturating.
Well,
so you're looking at more.
Yeah, I think it's more technical also. If you think about it, like in 10 milligram per kilogram, you're looking at about 13 nanogram per ml or 10 nanomolar concentration. Those are really low. If you don't have a good detection limit, your like 13 and 7 may not be different, right? So you can have your plot can be all over the place if you have very low concentration. That is what is happening for the low penetrant compound. That is what you are seeing. So at 100, you don't have that problem. You have very high concentration. And also you're right. You are saturating the metabolism pathway. You are just looking at the equilibrium transportation of the BBB. So that may be good, because realistically we are not using 10 milligram per kilogram for the efficacy studies. So we are using more like 100 milligram per kilogram for efficacy studies. So maybe it is better to look at the 100 milligram per kilogram for BBB.
So you're thinking the 100 mix, like typically you'll add one of those PGP inhibitors sometimes to actually look at the real permeability of the compound. So you say maybe dosing high, kind of serve as like you just saturate the transporter and then look at the intrinsic permeability.
Maybe, but also you have to think about the metabolism, right? So the compound metabolism. So it's a dynamic process. It's not just one process going on there, right?
So at a higher dose, you would likely be overriding the stability of the compound, so the microsomal stability, so that more of that compound can actually reach the blood-brain barrier at the end. Versus a 10 milligram per kilogram dose, most of it might be converted if it has very low stability.
That's a good point. The other question I have, could you use the in silico model, just take all of the compounds in the database that we've made, and then just map out a prediction profile, just to see which one would predict good? That would be good. That would be a good exercise to do.
Of course.
Okay, thank you.
Thank you.
Very nice.
Very much.
Good job. Any other questions from Danny? If not?
I do.
Oh, sorry. I'm not going to get away that easily.
Sorry. I was wondering if this lady, I don't remember the name, if she...
Sani.
Okay.
That's the easy name.
It was very good talk. Thanks.
Thank you.
Whether you analyze or you consider the plasma binding data to see, to do the ratios, the brain to plasma ratios of the unbound part of the drug.
No, we haven't.
So that's a good point, Engel. So in this model, or what we are doing, what she is doing right now here is just the pure permeability we're looking at. But you are absolutely right. We are gathering those information, plasma binding, and also some lead compound. We are getting the brain tissue binding also. So yeah, those free fractions are something we need to consider for going forward. What is the free fraction you have for the activity? So, but for the if you are looking for a pure transporter, just the crossing the BBB, maybe it is not important. But you're right. At the equilibrium, it will be important to know what if it is partitioning from the plasma to brain, if the binding is different. So there is one more factor. But this assay, what Mehak is doing right now, is just looking at the permeability.
Okay.
It's good. Thank you. All right. Thank you. Next up is Lisa. You all right? Lisa, are you there?
Or do we want to go back?
Or should we go back to Alex? Alex? Still can't hear them. Alex? Jean-Fou?
Are they on?
They're here. Yes.
Hello?
They're here. Alex and Jean-Fou are there.
Alex? Jean-Fou?
Oh, no.
Oh, they're out. Oh, no,
no,
they're there.
Uh-oh. There's a problem with Brexit.
Yeah, it's the UK. It's just separated from Europe now. It drifted away, so.
Uh-oh. That's a very sensitive topic. Be careful. Lisa, are you there?
I think they're all. Are they the same?
Huh? No, I think they're all different. Alex and Jean-Philippe at SGC.
Okay.
Lisa is at ICR.
Oh. So there is a chat.
Is Lisa on?
There is someone who wrote.
So there's managed participants at the top. If you go ahead and look.
Huh?
They're up, yeah, up, further up. It's a drop down menu.
Oh,
Oh, there it is. So look at how many participants are on there.
14, yeah.
Yeah,
Alex and Jean-Philippe, yeah.
so they're mute. So Angle is mute. Alex and Jean-Philippe is mute.
No,
No, no,
Oh, no,
that's the camera.
That's the camera.
But the microphone should be on.
You can type a message to them to see if they can hear you. Someone did, yeah.
Julie just tried to them.
Huh?
Yeah, Alex and Jean-Philippe, can you hear?
Who texted them, is it?
Yeah, someone, Julie Owen.
What if you go to Alex and go and unmute on it?
No, they are.
They are muted.
Okay.
No, and the
Yeah, muted?
Yeah. Don't.
Click.
All right. Look, there's still something going on. Ooh.
Hello? Uh-oh.
All right. Who else do we have that we can work on?
Yeah, it was Lisa and Jean-Philippe. Hello?
Hello, this is Lisa. Can you hear me?
Yes,
Oh, yeah,
loud and clear.
Okay, brilliant.
Your system's working great. And yeah, later on, can you run on up to Oxford and see if you can sort out Alex and John?
So what are you doing now to get it?
She needs to.
Can I close it? This one or?
Yeah, close it, yeah, suppose.
I'll just minimize?
Yeah, either is fine.
Okay. We got to Lisa. Yeah. Okay, comme les piquets, Jean, so we'll let Lisa go for now. So Lisa, you're up.
Yeah, thank you.
And I can do your slides. I don't know if you want to drive your slides or you want me to drive them for you.
Probably best if you do. I'll tell you when to change slides. That's fine. Actually, you can go to the next one already. Yep.
Okay, there we go.
Okay, so just to introduce myself, because I've not spoken at any of these meetings before, I recently started a fellowship at the Institute of Cancer Research over the summer, and I'm retraining as a computational medicinal chemist. And the aims of my project were to provide strategies to overcome some of the issues that existed with the ALK2 compounds, such as the hERG activity with the pyridine series. To ensure that we had brain penetrant compounds, to maximize the selectivity over the other ALKs, and just generally to support the project with any questions that might sort of arise over the course of the project. So if you go on to the next slide, I'll go on to what I've done with the hERG analysis. Now, in the pyridine series, there was data for 36 compounds, so that's Q-patch data, with a range of IC50s from sort of fairly potent at 0.8 micromolar up to sort of inactive at greater than 50 micromolar. Now, I did sort of a bit of a crude analysis of the hERG data against sort of individual physicochemical properties. There wasn't a particular link to any individual property. You know, the compounds, most of them possess quite a basic amine with a pKa around 9, and you know, some of them were active at hERG and some of them weren't. It was already known that compounds like M4K 2234 with this amide group managed to avoid having any hERG activity. Generally, these have sort of higher polar surface area. No particular sort of trend with the lipophilicity of the compounds with the log P. I guess generally might want to keep them sort of below 4. So there's no sort of obvious link with one particular property. So I did do a little bit of investigation, if you go on to the next slide, at doing some quantitative structure activity relationship models. Now I think, you know, these are sort of notoriously difficult for sort of predicting hERG, but sort of in a position where I'm sort of here to learn about these things as well, I did have a go. And certainly there were some classification models where I sort of called anything which had activity less than sort of 15 micromolar as something that bound, and anything sort of over 20 micromolar as something which didn't, and also regression models using the data. And whilst I could find models where the statistics suggested they were quite well fitting, I didn't necessarily think that these were anything particularly useful for the project. You could take compounds which look quite similar to ones that you already had, for example, ones which possessed the amide like 2234, and it would say it would be inactive. But I think, you know, medicinal chemists already know this. And then if you took any compound which sort of differed more greatly from what was used in the set to build the models, sort of things like the pyridol, the Novartis type pyridol compounds, or if you took compounds which instead of having sort of the aryl had the thiophene, and I think Diva was making some versions like that, the predictions actually vary depending on which model you looked at. And to be honest, I don't think I had a lot of confidence in sort of the output for those. Now, I know at the moment HERG's not seen actually as great a risk as probably when my proposal for this fellowship was written, but certainly if there is any new HERG data, it may help to provide, may help to improve the models or provide some confidence in the models. But I think it's the sort of point where I think I will sort of leave that for now. But what I am doing instead is just doing some fragment replacement searches around the amide. So these are sort of searches which look for similar sort of shape and electrostatics. And it might give some sort of new ideas as to what could be done around there. So I'll be analysing those, having a look at the results that come up, but then sort of the properties for those compounds and where they sort of fit, and doing some docking, and then I'll feedback it if there are any sort of new and interesting ideas which come up around that. If you go on to the next slide, I've also done a little bit of analysis of sort of the blame to plasma ratio. I guess I'm more looking at this from a perspective of trying to identify what sort of physicochemical properties might be sort of driving that, to help sort of identify what type of compounds we should be making in future. There was data on, at the time, 15, or probably still now, 15 compounds, and this is across both series. And the only trend that I could kind of see with these was that compounds which have a higher molecular weight tended to have quite a low in vivo brain to plasma ratio, and these are tended to be the blueprint compounds. And so it might be quite interesting to see the compounds that I think are being made at Charles River from sort of the second blueprint patent, which will be a bit smaller, and see whether that can sort of improve the brain penetration of those compounds. Probably the ones on the graphs I had on the right hand side there, I did have a look at how it compared to sort of the permeability and the efflux data, but I think the previous presentation has shown probably some more sophisticated data than what I've got there. But generally compounds which did have high passive permeability and low efflux did tend to show higher in vivo ratios. So again, there's not sort of a great deal more work I can do in this area. So what I'm moving on to now, and I thought I'd just sort of present some of the things I was looking to do. Partly also because I suppose being fairly new on the project, I just want to make sure that it's not something that's been investigated by someone before. So if we do go on to the next slide, I've got just a little bit of my explanation of sort of what I was going to be looking into with regards to selectivity over the other ALKs. So the aim of this part of my fellowship was to sort of rationalise the selectivity of compounds for ALK2 over across the range of all the other ALKs. And what I'm sort of showing in this picture here is M4K 2009, which does not have sort of a great selectivity over ALK6, and that is docked into ALK2, and then I've overlaid it with the ALK6 structure. On the right-hand side, I've taken the blueprint compound, and from the data that blueprint show on their compound, that is supposed to be quite selective over ALK6. And again, I've docked that into ALK2 and overlaid it with the ALK6 structure. Now you see on the left-hand side, 2009 fits quite nicely in the binding site, both of ALK2 and ALK6. Whereas on the right-hand side, this tyrosine 215, which is present in ALK6, sort of in a bit of a different position to where it is in ALK2, sort of closes off the binding pocket a little bit. And where I've drawn the arrow, there's a bit of a clash between where the blueprint compound sits and this particular tyrosine. So it's a suggestion as to how the selectivity may be arising, sort of difference between these two compounds. But I was going to do a bit more work around here. Certainly there are, there's a quinazolone series that was worked on here at the ICR previously, which was actually quite potent against ALK6. And also just trying to understand what it is which is driving these differences in the two structures, the ALK2 and the ALK6. I have identified some intramolecular interactions within the structures which may be giving rise to this. And just sort of what the implications are sort of for the other ALKs as well. For example, it looks at from the sequence of ALK3 that you'd have a very similar structure to what you have here for ALK6. So I guess this is kind of something that can turn into quite sort of a large piece of work looking at across all the different ALKs. But certainly if anyone has already analysed any of these in any way, please do let me know. And just lastly on the last slide, as I said, I'm happy to sort of investigate if any research brings up any questions which could be answered by sort of an investigation of the structure or any sort of computational modelling. So in the last meeting, Alex was showing the data where the pyridine series and blueprint compound showing their binding data against the ALK2 mutants. And while the pyridine series inhibited all the ALK2 mutants equally, the blueprint analog instead bound just the G356D mutant quite poorly. So this is just something I just popped together today. So Alex sent me his model of the ALK2 G356D mutant, and I've just overlaid that with the structure of 3007, so a very close analog to 3078. So ALK2 has the DLG motif shown in green, and the mutant, that's the DLD shown in orange. So you can sort of see, if you look at the aspartic acid 356 compared to the glycine 356, you can see that aspartic acid kind of moves into the space that would otherwise have been towards where the aspartic acid 354 is occupying in the ALK2, and in the mutant that sort of pushes the aspartic acid 354 towards where the blueprint compound is sitting in the binding site. So this, I guess, starts to suggest why the blueprint compound might not be, or that series may not be active against this particular mutant. But I think I need to look at this a bit more and certainly look at how the pyridine series compares as well. So check whether this also wouldn't impact on the binding of the pyridine series. So yeah, that's what I had.
Hi, Lisa.
Thank you. Any questions for Lisa? Thank you for that summary. Very good.
Hi, Lisa. This is Nicole from Charles River.
Hi.
Hi. Really nice work. I was just thinking the mutant work is actually quite interesting, and it's maybe not something we thought of. We've had some computational chemistry support here, but we haven't done that yet. I was just wondering if you could build homology models for some of the other mutants where we don't have crystal structures available.
Yeah, so so far I have built homology models for some of the other ALKs. So for example, ALK3 from ALK6. So yeah, I suppose I started building my own model of this particular mutant, and then Alex already had one. So yeah, I assume that is something we could look at. Yeah.
Thanks. I think that'd be useful.
Yeah.
That's good. Okay, if there are no other questions for Lisa, we could try Alex again and Jiangfu. Are you guys online, sir? Alex? Jiangfu? Wow.
Matt, they sent you a message. Did you read it?
Oh,
Yeah, I'm
Under
reading
chat, in the chat section.
Chat.
I think they were asking you to summarize their slide.
Go down.
Okay. Yeah, down. Okay, I'm looking for the chat section. Do I need to exit?
Pull down menu. Then the green, goes over to the green.
Okay.
On the bottom, Mats.
And the bottom, manage participants? Yeah.
I think you might need to stop.
Yeah. Stop share first. And there's the chat.
The chat.
Orange. I think they've been setting up flames for a while.
Troubleshoot, right? So, you listed
What?
Oh, go on. Oh, yeah, there.
Oh, okay.
Perhaps you could summarize one slide for us from profit. Okay. We were there in from your muted the
This was, yeah, okay.
Yep.
Hi.
Yep.
How are you?
We're gonna take it.
So are you trying to pull out our?
Yeah, we just pulled up the chat. So what they've asked you to do is just
Just summarize this, right?
the contact binding components slide. So can you?
Yeah, I could do that.
Do you want to pull up?
It's okay, yeah, that's good. They have the slide up already, yeah.
Which slide is it?
The one, the FDC one, the green,
This one?
no, next one. That one.
Okay, I'll let you slide.
Okay. So yes, I guess today I'm Alex and Jean. Okay, so this is some update. I mean, John just came back from vacation, so he had some work that he had done. I just asked her just prior to him leaving. And he had run some of the PROTAC compounds back to the nanogrid to kind of confirm the cellular activity, because that's always one of the concerns with the PROTACs is whether or not you're going to get good cell-based activity. And so, just for summary, so last week we had, so of the 4 PROTACs that we have made so far, you have 2241. You could see the nanogrid first time around wasn't that great, it was about 3 micromolar. Whereas, you know, when we actually replace that with a more lipophilic linker, so 2268, we're getting about 800 nanomolar activity in cells. But then 3102, this one was from Charles River, that compound was looking very good previously. We got about 20 nanomolar. And now on repeat, they were getting about 143. Now to make the point, 2268, the one that we made that was more lipophilic, initially was 800, now second time around it's running about 200. So maybe those two compounds are actually practically almost the same in terms of the cellular activity. So these PROTACs, they're getting into the cell. So one of the key things going forward, if you could really find a good antibody just to kind of identify when the protein is degraded or not, that's one of the challenges right now. These might be some good compounds to sort of assess that.
One question there. Are they going to do the negative control of 3103? So the other enantiomer of the VHL ligand?
I mean, we didn't make it, we could. I mean, if you find one that starts giving us action in the cell, then that would be a good negative control to actually validate that. So, you know, but they have no good headache. First, we were getting good binding biochemically. We were questioning, are we actually going to see activity in the nanobretin cells? The first couple of ones we made were very weak. These newer ones actually are sub 500 nanomolar, which is not bad. Now, our challenge right now is there is no good antibody for us to look at degradation. And as soon as we start getting into degradation, we need to do the negative control. I agree.
But the other thing is, what is the median life of the ALK2 in cells? Because if it's less than 8 hours, then the PROTAC is not going to be.
Yeah, all those are properties we really need to characterize for ALK2 degradation.
Yeah, because if not.
Yeah. Those need to be done. You need to understand the turnover for ALK2 too. Yeah. Okay, so that's basically the summary we had for today.
I had a quick thing from Nicole here again, just on behalf of the UK. So Alex can't speak and Sue can't, but they've messaged me to say that they've found some new antibodies for ALK2, and between Charles River and SGC, we're trying to validate a panel of antibodies now. So I think hopefully by the next meeting we should have some data.
Okay, that's fantastic.
Great.
Yeah, good news. Thanks, Nicole. That's good. If not, I think that's, you know, all the presentation for today. Excellent update. Thanks, everyone.
So just one thing. So for the November meeting, Al and I are now planning to attend from Cambridge. So you'll be hearing us pestering you from the line rather than in person.
Yeah.
So hopefully it should be a good time for the meeting, because a lot of these programs are starting to wrap up from this initial stage, but also it's a chance to start thinking forward about what we're going to do both into the no-cost extension period of about 6 months or 4 or 5 months, and also as the program continues on from there. So.
Okay. Thank you, everyone. If there are no other questions, see you next month. All right. Take care.
Thank you, everyone. Even if the UK lines were down today.
Bye. Thank you.
Okay. Bye.
Go to the chat and hang up on me. Go to the chat.